Association. I've just got a few announcements and then we'll begin our presentation. I've got on this screen here, we have our call for abstracts open for our 2025 conference. The conference is scheduled for September 25th, and it will be held in Denver at the Colorado Department of Public Health and Environment. We've got the topics of interest listed here, and you'll reach out to submit abstracts at our Gmail here, and it's all on our website, and I'll drop the link in the chat here in a minute. But we invite folks on the call to submit an abstract or join the conference. We'll have registration posted soon as well, and there will also be sponsorship opportunities and opportunities for companies to exhibit as well. Okay. And we have another Lunch and Learn coming up next month. So if you're not on our email list, reach out and we'll get you added. And then one more announcement is our scholarship program. The application period will be opening in the next couple of weeks. So we also will post that on our website and send out announcements over email as well. Okay, and those are announcements I've got for you. So I'd like to introduce our speaker today, Professor Jeff Collett. And we're excited to have him present. He's been working at Colorado State University for the past 30 years in the Atmospheric Science Department, and he is ranked as Distinguished Professor at the university. Professor Collett holds many prestigious positions, including being a Fellow of the American Meteorological Society, and he is the Chief Editor for the Journal of Air and Waste Management Association. And one more note is that we're in part connected through our scholarship program. So this year we actually were able to award one of his students our section scholarship. So really great to have the community connected this way. All right, I will go ahead and pass this over, and I'll just also note that we'll hold questions till the end. He'll present for about 45 minutes, and then we'll pause for questions.
She sent out a survey, and I responded to the survey.
Make sure that you're all muted. Thank you.
If you have a question, feel free to put it in the chat during the conversation, but we'll make sure we save time at the end. All right, take it away, Professor. You're just on mute there still.
All right, sorry, I couldn't get back to the mute thing once I was presenting. So let me get this going again.
Great, we can hear you and see your screen.
Perfect, all right.
Thank you.
So thank you very much. It's great to have the opportunity to talk to so many of you. It's great to see so many people on the call today. And I'm going to be telling you really 3 stories of different work that we've done looking at air quality impacts of oil and gas development, one focusing on haze, one focusing on ozone, and the last one focusing on air toxics. So professors aren't usually the ones that do all the great work that gets published and presented here. So I want to acknowledge many of the folks that have been involved in this, students, postdocs, research staff at CSU. I've put a few pictures up here of some of the key people, Ashley, Yiting, Andre, and Da, who have done a lot of the work that I'll be presenting to you like to also acknowledge some of our collaborators at the National Park Service and at Ajax Analytics that we've worked with on different studies, and then the funding for the work that I'll present, which comes in different cases from the National Park Service, from the City and County of Broomfield, and from the Health Effects Institute Energy Program. So probably most of you on the call are well aware that the US is, for the last decade, the largest producer globally of oil and natural gas. And this has come about because of improvements, especially in directional drilling and hydraulic fracturing techniques that have made vast new oil and gas reserves economically accessible. And this happens in different plays across the US. Today, for our three stories, we're going to start up in the Bakken oil patch in western North Dakota and eastern Montana. We'll then move down to talk about ozone in the Permian Basin, looking at Carlsbad Caverns National Park. And we'll finish up here in Colorado in the Denver-Julesburg Basin, looking at issues around air toxic emissions and exposures. So before we jump in, I like to think about the different potential issues related to air quality impacts of oil and gas development as divided across different spatial scales. So if we think about, for example, emissions of methane, this is long-lived in the atmosphere, an important greenhouse gas, of course, but it gets distributed over its lifetime globally. And so those effects really are global. It doesn't matter exactly where the emissions are happening. If we think about regional air quality issues, though, like ozone or fine particles, these are both secondary pollutants in the atmosphere. Here, the spatial scales that are most relevant are from maybe tens up to several hundreds of kilometers. It's different with air toxics. Here, if you think about something like benzene emitted directly from an operation, that gets diluted pretty quickly as it moves downwind from the source. So the highest exposures are likely to occur very close to the operations. And so here we might think of spatial scales from meters up to maybe a few kilometers or so as being the most critical. So we're going to start with a story about fine particle and winter haze formation. Here we're going to focus especially on the formation of ammonium nitrate particles. These are submicron particles that form by reactions between nitric acid and ammonia. Nitric acid is formed by oxidation of NOx emissions in the atmosphere. It's in the gas phase. Ammonia has a variety of sources, but the biggest ones are agricultural in nature, also in the gas phase. But when these two compounds react, they go on to form a particle. And those particles, being in the submicron size range, are similar in size to the wavelength of visible light. And that makes them really effective scatterers. And so they really contribute to the formation of haze and visibility degradation. And if you look, for example, here on the Front Range in the wintertime, you see a lot of ammonium nitrate haze also being formed. This picture comes from the Bakken oil patch. You can see some of this haze here. We tend to think most about this situation with ammonium nitrate in the winter. The particle formation is reversible, but this equilibrium shifts towards the particle side when temperatures are cold and humidities are high. So this tends to be primarily a winter phenomenon. So why did we go to the Bakken to look at this? Well, the National Park Service had been looking at trends in concentrations of different aerosol species across time. And I think I saw Jenny Hand here on the call. She actually put together this figure looking at trends, in this case, between 2000 and 2013 in the month of March in fine particle nitrate concentrations. And what you can see is across most of the country, there were on average decreases of up to several percent per year in March nitrate concentrations. And this was stemming from large reductions in NOx emissions. But you see some exceptions to that pattern, especially this bullseye up here in western North Dakota and eastern Montana. If you take a look at a nighttime satellite view, this is a VIIRS satellite view, you can see all these different big urban areas like Chicago or Denver or Southern California. But you also see other regions like here in Western North Dakota and Eastern Montana, where you have what looks like a major urban area. But of course, there is not a major urban area there. This is really the lights from the well pads and the flares that were burning at this time about a decade ago when this image was taken. So if you look at the production, in this case, just in North Dakota, of oil, you see that really starts ramping up in 2008 quite rapidly in the Bakken oil patch. So the Park Service was interested in and concerned about impacts on national parks in this area, including Theodore Roosevelt National Park. And we hypothesized that the NOx emissions from the oil development and the infrastructure supporting that might be contributing to this increase in late winter nitrate formation. So we spent 2 winters up there looking at air quality issues and that might be associated with the development of oil and gas. This sort of darker brown shading, these are the oil wells. These colored circles are our monitoring sites. Our most intensive measurements were here at the north unit of Theodore Roosevelt National Park, which sits in the heart of the Bakken oil patch, and most of the data that I'll show you come from there. We looked at aerosol concentrations, we looked at volatile organic compounds, or VOCs, we looked at precursor gases, like we talked about ammonia and nitric acid, in particular, methane, and so forth. So I'll show you just some mobile measurements that we made. These are of methane. We were driving around, and you can see here in yellow now the North Dakota side of the border where the wells were. And you can see we often ran into elevated concentrations of methane as we moved throughout this region. But we also drove in other regions without oil wells. And you see, for example, elevated methane over here too. But if we look at other species and we collected samples of VOCs along these drives, you can see ethane is elevated in this oil production region. But over here, this is really biogenic methane from wetlands in this region that's being produced, and therefore we don't see ethane. So we can use different VOCs to distinguish between different sources, in this case of methane. So we'll take a look at some of the particle measurements. Remember, we were going there especially to look at this winter haze issue. And here you can see high time resolution measurements made starting in November and continuing into March of different species. These are made with an online aerosol mass spectrometer, and the colors indicate different species. And a couple of things I want to draw your attention to is sometimes it's pretty clean, right? We see something like a microgram per cubic meter of PM2.5 that's speciated in the mass spectrometer. But we get these rapid transitions where concentrations build up quite strongly over a relatively short time. And often these peaks have a lot of ammonium and nitrate, consistent with this reaction between nitric acid coming from NOx oxidation and ammonia. Here's a little bit different look at it. These are from daily filter-based measurements of particle composition. And so you don't see quite the same time resolution here. But if we look, for example, in clean periods like this one here, and we look at the transport of air during that period, we see that typically during these sort of clean periods, we have very fast transport coming out of the west. So presumably all of the local emissions are just being blown away quickly before they react and build up. During periods where we get stagnation or recirculation over the oil patch region, however, we see these buildups in the fine particle concentrations, often ammonium nitrate, sometimes some sulfate as well building up in there. So one of the things we did using our VOC measurements was try to get an idea about the age of the emissions in the atmosphere that we're reacting to result in this issue. And so here we use the conversion atmosphere by reaction with hydroxyl radical in a number of steps. And we know the rates of this chemistry pretty well for different alkanes. So we can look, for example, at the formation of pentyl nitrate and butyl nitrate, and we can establish a sort of chemical clock where we can look at those species in our samples and determine how long those compounds have been in the atmosphere. And what I want to draw your attention to here is when we have the highest PM2.5 concentrations, we typically have these emissions in the atmosphere for less than a day. So again, this is consistent with local formation versus long-range transport and consistent with those rapid buildups we saw in the PM2.5 concentrations. So finally, I'll mention we did some modeling of this system. We used an aerosol thermodynamic model that looks at the chemistry, for example, of ammonium nitrate and ammonium sulfate formation and other species as well. And we looked at that. You can see here hour by hour measurements of these different species treated in the thermodynamic model to look at the sensitivity of fine particle formation to concentrations of different ingredients in this chemistry. And on the left, we have the sensitivity of PM2.5 formation to ammonia addition. And on the right, we have sensitivity to nitric acid addition. Over here at the right, you can see the average sensitivity for those. So in the winter up there, we tend to be quite ammonia limited. There aren't a lot of agricultural emissions in the winter. Ammonia concentrations tend to be fairly low. So we're very sensitive to addition of ammonia on average. We're less sensitive to adding more nitric acid on average. But if you look as a function of temperature, you'll see that ammonia sensitivity is highest when things are really quite cold in the heart of the winter. And the nitric acid sensitivity increases as we move into sort of the winter shoulder seasons, for example, that month of March. So during this period in particular, when things are a bit warmer, we have more ammonia around, we see greater sensitivity to NOx emissions and to nitric acid. All right, so that's our first story, looking at influence of NOx emissions in the Bakken on winter haze formation. For the second story, we're going to move quite a bit south down to New Mexico to Carlsbad Caverns National Park, and we're going to focus on the summer and look at ozone issues. This is a picture taken from Carlsbad Caverns National Park, looking out over the Permian Basin. You can see the lights of the oil fields and the flares actually quite close to this national park. So again, the National Park Service was getting concerned about potential impacts of this development on air quality in the national park. So to situate you a little bit, here's Carlsbad Caverns National Park down in southeast New Mexico. This is the Permian oil and gas basin. This is now the largest oil producing basin and the second largest natural gas producing basin in the US. The blue dots in here, these are the wells throughout this region. And over the last, 15 years or so, if you look at the record of ozone concentrations measured in Carlsbad Caverns National Park, you see that they've been increasing, especially in recent years. And during the same time period is when a lot of the development of the oil and gas wells and the production in the Permian has been ramping up. So oil and gas operations will emit both nitrogen oxides and VOCs, as we talked about in the Bakken. And as many of you surely know, those are the key ingredients in the presence of sunlight to form ozone in the atmosphere. So we really wanted to try and understand these changes in atmospheric composition in the national park adjacent to the oil and gas region, and how they might be contributing to ozone there. So we actually did 3 different studies down there. A first sort of pilot study was in 2017. The study I'll tell you about today was in 2019, and we had a smaller follow-up study in 2021 that we're currently analyzing data from. So to give you an idea about the emissions in this region, this is a satellite view of NO2 columns in the atmosphere. And here is our measurement site in Carlsbad Caverns National Park. So you can see a lot of this NO2 in this Permian region in both the Delaware and the Midland basins. But you see there are other sources. Of course, there are other basins in Texas and in Oklahoma, as well as urban areas like, for example, El Paso over here. In terms of VOCs, in 2017, we collected samples across a number of parks in the Southwest US over several months. And here you can see, if you look at the diamonds, these are the total canister concentrations of VOCs we measured. You see they're much higher in Carlsbad Caverns National Park than in these other parks like Grand Canyon or Joshua Tree, which sits downwind of the LA Basin. You also see that this blue bar is quite large. This is the alkane fraction of the VOCs. And oil and gas operations, not surprisingly, emit a lot of alkanes. So we typically see this in oil and gas dominated VOC emission regions. So in 2019, we took a lot of equipment down there. We were measuring nitrogen oxides. We were measuring, of course, ozone. We were making online measurements of a broad range of VOCs. We also looked at aerosol chemistry and haze in that region as well. And we have a lot of data. Just to give you an idea, we were there from late July into early September, and we have data hour by hour on things like VOC composition, NO, NO2, more oxidized NOY, of course, ozone, and so forth. So I want to highlight a few things that came out of this study. The first one I'll show you is our analysis of the different VOCs. So we measured about 50 different VOCs there, hour by hour. And we used a statistical tool called positive matrix factorization, or PMF. If you're not familiar with this, you might be familiar with principal component analysis, which is kind of similar. But basically, this is a statistical tool that looks at the covariance of these 50 different VOCs in time to look for which things move up and down together and to identify different factors that explain the variability in the data set. And we interpret these factors as representing different sources typically. So when we did this PMF analysis for the Carlsbad Caverns data set, we ended up with 7 different source factors, and 3 of these had compounds that led us to associate them with oil and gas emissions. So lots of lighter alkanes and lots of heavier alkanes broke out into 2 factors. These are very typical to see in oil and gas producing regions for this kind of analysis. We also saw a 3rd factor that had a lot of really heavier alkanes, like C8 to C10 alkanes. We called this here process-specific oil and gas because, as I'll show you in the Denver-Julesburg Basin, we have good evidence that a lot of these emissions come from drilling operations in particular, but they could come from some other things as well, oil and gas related. So if you take some of these factors and you look at when they're most important, you see, for example, for this factor 3, the transport is most likely to be from the southeast when we see a lot of this factor in our data at Carlsbad Caverns. And this is really over the heart of the Permian Basin. If we contrast that with, say, this background factor, which contains biogenic emissions, acetonitrile, which might be long-range transported smoke, and so forth, we see that that's more likely when we get transport from other regions other than the basin. So we were, of course, really interested here in trying to understand ozone formation. So Andre Marsevan, a student working with me, did some really nice modeling of the ozone chemistry in this region. And he used a box model, which is simple in terms of spatial or dynamic representation, but quite sophisticated in terms of the chemistry. And unlike regional chemical transport models that are often used to simulate ozone, here we don't rely on emissions inventories for the inputs to the model. We actually constrain the model simulation using the local observations of NOx and speciated VOCs. So we avoid the uncertainties that are always inherent in using emission inventories. And so Andre ran this model for a broad range of levels of NOx and VOCs. It's easy to run this model over and over for different conditions. And in this diagram, this is a summary of the maximum 1 hour ozone as a function of NOx and VOC levels, where this point in the center is the observed levels, in this case for the average of 11 days that we modeled. And so you can look at this and say, well, what happens if we increase or decrease, say, VOCs, or we increase or decrease NOx? What does the model suggest will happen to ozone in this environment? If you don't like this sort of contour, you can look over here at the right. These are individual days where we scale NOx or VOCs. And the main takeaway from this is if we decrease VOCs or NOx, ozone is expected to go down. But for the average conditions here, the system is more sensitive to NOx emissions. You fall down this hill more quickly if you reduce NOx than if you reduce VOCs. So we can look at this, of course, a little bit more quantitatively. And here we looked at, for example, a hypothetical 20% change in NOx or VOC levels in the basin. And here we didn't just move all VOCs up or down. We used our PMF factor analysis to move up and down VOCs associated with different source types, including the oil and gas specific sources. And what you see here for NOx is that you get more bang for your reduction or increase in NOx than you do for these different VOC groups. But if you put the oil and gas VOC groups together and think about decreasing or increasing them by 20%, it's still a significant change in ozone levels. And more importantly, if you combine these strategies to, say, decrease NOx and oil and gas VOC emissions together, you get a better return in terms of improving ozone than you do from doing either of these things alone. All right, so that's our second story. And our final story, we're going to come to Colorado, to the Denver-Julesburg Basin. And we're going to ask, if you go and you talk to somebody who's living in a house like this one, that's close to a new oil and gas well pad that's being developed or perhaps already in production, what are they likely to be most concerned about in air quality? Well, they may care about climate and methane. They might care about regional ozone and fine particle concentrations. But most likely, if they're really living close to these well pads, they're thinking most about what their exposure might be to air toxics like benzene. So here we're going to look at data from two different studies. The first one is work that's sponsored by the City and County of Broomfield, and this is conducted in partnership with Ajax Analytics. And here, over now several years, we've been monitoring across the community VOC concentrations, starting in late 2018, prior to the development of 6 large oil and gas well pads in these orange rectangles here on the map. We had monitoring of VOCs close to these well pads, at community sites further away, and at another background site a few kilometers away, to look at how VOCs in the area were changing as these well pads were being developed. Again, this work was sponsored by Broomfield. We were taking weekly canisters at these different locations, and we also used PID, or photoionization detection sensors, that continuously monitor VOC levels sort of semi-quantitatively in the atmosphere, but can be used to detect plumes coming across the sensor and trigger collection of a canister to do more quantitative detailed speciation of VOCs in those transient plumes. So we've been monitoring, we're still monitoring in Broomfield at fewer sites now, but in the height of development, we had as many as 18 different monitoring locations across the community. The other study that I'll talk about results from is one that we're just wrapping up now. This is sponsored by the Health Effects Institute, looking at, again, air emissions, especially air toxics, from development of oil and gas well pads. In this case, we looked at 3 different sites, one near Aurora, one near Brighton, and one near Windsor. There were 4 well pads at those sites. And we worked with 3 different oil and gas operators to get information about pad operations to compare those to what we were seeing. And here, the state of Colorado graciously helped support this study by bringing out their mobile monitoring lab. The CAMEL did online hourly speciated VOCs. Again, we had weekly integrated VOC canisters and PID sensors that could detect plumes and trigger canisters to look at transient plume concentrations. And we did some mobile measurements as well. So what we were really interested, both in Broomfield and in this HEI study, was what happens as the wells go through, the well pad goes through different stages of development. And those of you that are familiar with this space know that, you know, the equipment changes a lot as you go from drilling to fracking and on to flowback and so forth. The contact between the subsurface hydrocarbon deposit and the atmosphere also changes a lot for different operations. For example, during drilling, you're bringing material back up the wellbore and you can get volatilization and venting to the atmosphere. Whereas during fracking, you're generating a lot of power on the surface, which has its own emissions. But as far as the well, you're really pushing material down and pressurizing that well. So we don't expect to see a lot of subsurface emissions there. So let's start with some data from Broomfield. This is from the second pad developed in Broomfield called the Livingston pad. And what we're looking at here are timelines. The 4 panels are different VOCs or groups of VOCs. And the colored bars are different operational timescales. So you can see drilling, fracking, coiled tubing, which is when they go in and they mill out the plugs that separate the stages for stage by stage fracking. We get some ventilation to the atmosphere of VOCs at that point. And then flowback, where the injected and formation produced water come back up out of the well before tapering off and the well goes on into production. And each of these plots is looking at the local excess concentration of some. So for example, here, these are these larger alkanes, C8 to C10 alkanes, so octane, nonane, and decane. And we're looking at the concentration close to the pad, subtracting the background concentration from a few kilometers away. So we're looking at the influence of the pad on the local air quality. And you can see here, for example, during drilling, we get a large increase in the concentrations of these heavier alkanes. We also see ethane and benzene, other things go up as well. But the signature is really quite clear here. During drilling of this pad, they were using NeoFlow, which is a synthetic drilling fluid. So that's used to mix up the drilling mud that lubricates the drill bit and helps move the drill cuttings back to the surface. That is increasingly used in the DJ Basin and elsewhere because it's much lower odor than traditional petroleum-based drilling muds. But we do see these large emissions of, for example, nonane, which is an air toxic, and these larger alkanes are also more reactive and could be contributing to ozone formation as well. So the trade-off is probably still a good one, but the use of these synthetic drilling fluids aren't without some concerns of their own. If we look more broadly across Broomfield, now we're looking at just the total VOC concentrations here measured in canisters. And there's 3 lines on this timeline that just correspond to the minimum, the mean, and the maximum concentration we measured in our sites across the community. And what you see here prior to the start of well development, to the start of drilling, there's not much gradient in total VOC concentrations across Broomfield. Things are fairly uniform on a weekly average time scale. Once drilling begins, though, and these pads are going through well development, you see that these lines move apart, and the highest lines are the sites that are close to the well pads. So we definitely see during pre-production in particular, these local increases in VOC concentrations. In this case, there were 2 pads that were developed, and then things were shut down for some period before additional well pads were developed. And you can see during this production period, yes, there's some difference between these lines, but they tend to be much closer together than they are during the pre-production period. But once drilling starts up again at some of the subsequent well pads, you see the near pad concentrations pop up again. And we can do this, of course, we can look at this for any VOC. Here's the same plot for benzene. And you see the same sort of pattern where benzene concentrations locally to the pads pop up during pre-production and tend to drop back down when we're in a production phase. The good news here is that the benzene concentrations, even at their maximum, are less than a part per billion, quite a bit below the 3 part per billion chronic health guideline value for long-term exposure for non-cancer health effects. So this is good. We see increases in benzene, but they're not reaching up to these sort of health guideline value levels. Now, another thing that we did using this Broomfield data set, we had so many observations and we had all of these well pads going through development at different times, is that we could basically use an inverse modeling approach to take our ambient concentrations and determine what the emission rates were from different well pads undergoing different operations. And we have a lot of really interesting information from this analysis. I just will highlight 3 examples. So one is we have good estimates now for the emissions of VOCs from drilling mud volatilization, including this increasingly popular synthetic neoflow-based drilling mud. And here again, you see, for example, these high emissions of these larger alkanes from that. We have actually the first emissions of VOCs for the coil tubing or mill out operations when they go in and remove those frac stage plugs. If you look, for example, at the total VOCs, we see that the highest emissions are coming from drilling and from this coil tubing operation. So this is an area that needs some more attention. What you also see, though, and is quite a nice result, is that if you look during flowback, in a study a few years ago, we found the largest VOC emissions associated with flowback. That's represented by this X in this plot. What we saw in Broomfield, where they were using closed-loop tankless systems to help limit VOC emissions on the pad during flowback, we had more than a 95% reduction in both total VOCs and in benzene emissions on average relative to what we saw in other green completions just a few years ago. So this is a real success story in terms of the effectiveness of some of the newer approaches to limit VOC emissions during pre-production. So far for these data, we've been looking at the weekly average samples, and we saw that, for example, the benzene concentrations don't rise especially high in those weekly data. There is another side to this, though, and these are short-term plumes. So remember, we have these PID sensors that are continuously monitoring VOCs, and when they see concentrations go up, for example, here you see a big spike in the signal of that PID sensor, they can automatically trigger a canister that collects right away material from that plume that comes back to the lab and can be analyzed. So this timeline example that I have at the bottom here is from two PID sensors located close to each other. They both saw this plume and triggered canisters that were collected. These were collected during flowback operations at one of the pads in Broomfield, the United pad. And we measured in one of these canisters 819 parts per billion of benzene and 653 parts per billion of benzene in the others. These are the highest concentrations that we've seen in transient plumes in studies like this. Up here at the right, you can see 91 different canisters collected associated with plumes from different operations. These are those two I just mentioned. They're much higher than we typically see, but we do often see benzene concentrations between maybe 10 and 50 parts per billion showing up in some of these transient plumes. So while the average weekly concentrations don't increase so much around the pad, these plumes, which often cross our sensor for just maybe 10, 20, 30 minutes, do contain very high concentrations. And we need to think about the potential health effects associated with these short-term or acute exposure events. So I'll show you just a little bit of data from this other Health Effects Institute study. Again, the design is kind of similar to the measurements in Broomfield. We took advantage of what we learned there. And we have a lot of data from these different well pads operated by different operators for different activities. And we have information from the operators about what was going on the pads during the time of measurements. And we have more than 50 different VOCs that we can look at gradients around the pad at different time scales. So it's way too much data to look at. Let me just show you one example. So this is from the second site we worked at. These were drilling operations. And we can look here at the distributions of concentrations in our weekly canisters. At the right of each of the left side of this panel is our background site, a few kilometers away from the drilling operation. And then the other two concentration distributions are the near pad locations. So if we look, for example, at this site during drilling, yes, we see some increase, for example, in BTEX concentrations near the pad, but like in Broomfield, on a weekly average time scale, these are fairly modest in terms of the concentration increases. If we look at these short-term plumes, though, picked up by the PID sensor, again, like in Broomfield, we see concentration increases that are a factor of 10 or even 100 higher than we see in our typical background concentrations. So again, we need to think about the potential for acute exposure events from these shorter term plumes that are almost always less than an hour in duration, at least at a particular receptor point. So we've summarized all of the data from the Health Effects Institute study into sort of an acute and chronic exposure risk summary. Again, there's a lot of data here, sites 1, site 2, site 3. You can see different operations represented here. And you can see in these different colored boxes, the green ones are the weekly canisters that will compare to longer term exposure standards. The yellow and the blue are 1 hour measurements made by the CDPHE camel in blue and by our triggered canister measurements in yellow. And in each of these plots, we're plotting hazard quotients. So the hazard quotient is the ratio of the measured concentration to the health guideline value. So if that's a value of 1, where I've put this dashed blue line, that says that the concentration is at the health guideline value. And obviously, if you go above that, you're now exceeding that health guideline value, which might be some reason for concern. So what we see is all of the weekly data falls below the health guideline value. So we're below a hazard quotient of 1 for all of these green box distributions. We do see that nonane and benzene are both the biggest contributors out of the HAPs that we measured. But even together, they remain below this hazard quotient level of 1. When we look at the hourly data, we see that most of the time we're below this hazard quotient of 1. But for different operation types and at different locations, we see a few periods where these levels go above the health guideline value, suggesting that there could be some reason to think about the short-term exposures here. Now, one thing's important to keep in mind is we need to think about where these measurements are made. And so most of our measurements were made closer than Colorado's 2,000-foot setback distance. That's because we want to be close enough to the pad to clearly see activity emissions from that pad and to be able to relate those to the on-pad activities. For example, for our plume-triggered, our PID-triggered canisters at sites 1 and 2, which are represented here, we had measurement locations that ranged between 1,100 and 1,400 feet from the well pad. So what we can do is we can take a dispersion model. In this case, we use the EPA AirMod model we constrained that with our observed concentrations that we measured. We adjusted the emissions to match at that point. And then we used the AirMod simulation to extrapolate the concentrations to either closer or farther distances from the pad. And the good news here is that while we do see sometimes at our measurement locations concentrations above the acute exposure health guideline value, which is here at 9 ppb for benzene, we expect those concentrations to continue to drop at larger distances based on our meteorologically specific modeling that we had for these episodes. Suggesting that Colorado's decision to have a 2,000-foot setback distance is helping to be protective in terms of these acute exposures. On the other hand, not everywhere has a 2,000-foot setback distance, and sometimes Colorado grants exceptions to this. If we look the other way, as we go, especially inside 1,000 feet, we start to see increased likelihood of exposures at an hour duration that exceed the benzene acute health guideline value. All right, so those are our 3 stories. A lot of information, just a few key points to hopefully take away. One is that the U.S. has done a great job reducing NOx emissions from a lot of sources over the last 10 to 20 years. But growth in NOx emissions from oil and gas, we've seen, for example, in the Bakken oil patch, can offset some of those other source reductions and drive increase in winter haze formation from ammonium nitrate. We also see oil and gas development, for example, in the Permian Basin, being a key source of NOx and VOC emissions that can lead to increased ozone levels. And this certainly needs further scrutiny going forward. And then finally, if we think about exposure to air toxics, we typically see that it's more likely that acute exposures will exceed health guideline values than longer-term chronic exposures. And I'll mention this is consistent with CDPHE's 2019 health risk assessment, which was an important factor contributing to the decision to increase setback distances to 2,000 feet in Colorado. That study also found that it was the short-term exposures which likely were of more concern. The good news is that these exposure risks can be mitigated by, for example, increasing setback distances, such as Colorado did a few years ago. Increased use of electrified grid-powered drill rigs reduces emissions. And we saw especially the closed-loop tankless fluid handling systems have helped a lot in reducing average emissions during flowback. But there are still some weak points that need further attention. The drilling mud and the drill cuttings that come up out of the wellbore are hot. They're typically open. There's a lot of volatilization of VOCs that happens there. Even during flowback with these closed loop systems, you have to trap the sand that's coming up, the proppant that was used during fracking, and that gets opened up periodically. And we see these bigger pulses of emissions for short terms here. And there's some other things as well. But let me stop there, and hopefully we have some time and interest for some discussion and some questions.
Thank you so much. That was a wonderful presentation. We've got about 10 minutes for questions. If the audience has a question, feel free to put it in the chat or raise your hand, and we can have you ask the question here.
I have a question. Okay, well, I have two questions. Since 2018, you guys have been measuring in Broomfield. What key improvements or changes have you seen in observations over that time period? Has it gotten better? Have emissions gotten better or worse or changed a composition?
Yeah, so I would say the biggest thing is, once the wells went from pre-production activities, drilling and completions into production, we tended to see concentrations near the well pads went down for benzene and other activity-related VOCs. We also tended to see fewer of these high concentration short-term plumes. They didn't go away entirely, though. One thing I didn't mention is that maintenance operations can be an important source of emissions. So, for example, we saw a very high concentration plume, actually some distance away from the Livingston pad during separator maintenance. When you open up those separators, you're releasing material to the atmosphere, and we saw things increase quite a bit. Broomfield worked with the operator to try and change some of their maintenance operations to try and mitigate some of that. And we haven't seen as large of impacts during those operations as we did before. One thing we should look at soon is we're getting a pretty long record there, as you point out, Annarelli. We have a site that's not close to the well pads, and we really should look at what's happening there. We have week by week for, 6 years, almost 7 years now of data at that site. So we can use that as a long-term site, not oil and gas specific, but just sort of more regional measure.
That would be sick. The other question is, so those really, really high concentration plumes that were super short term, do you have any idea of the order of magnitude of concentrations for benzene that we are exposed to when you're pumping gas or when you're doing things near gasoline like that?
Yeah, we actually have a year of data from a gas station where we collected samples. These were, again, weekly average samples, so not short-term measurements. But we actually are looking quite a bit at that data now and looking at what the VOC composition looks like there relative to other places that we spend our time, right? Close to well pads, driving in traffic. So it's a really interesting data set. There is more benzene there, but it's not as high as you might think, at least on average. It's elevated, but it's not more elevated than we saw, for example, in the data I showed you from Broomfield in those weekly average concentrations. But there are other VOCs that are there too that we see. So
Perfect.
yeah, great question.
All right. Tom?
Thank you very much. Jeff, what a great overview of a large body of work. So I just wondered, in your various studies of the oil and gas basins, whether you notice a lot of sort of inter-operator differences in how the emissions behave at the sites. So you have different, business approaches by different operators and different procedural things. What kind of general conclusions could you comment on there?
Yeah, there really are large differences by basin. When we were working in the Bakken, I mean, this was still relatively early days in the development of the Bakken, and there were flares everywhere. There were ground flares where pools of stuff were on fire on the ground. They didn't have the infrastructure, especially at that time, to take natural gas away into to a sales line in much of the basin. So there was a lot that was being burned. So there are big differences there, but the difference, more recently between the DJ Basin and the Permian is also pretty big, right? It's unusual to see open flares here. Of course, we have enclosed combustors that sometimes are still doing something similar, but there's a lot of open flaring still in the Permian. So there are big differences in those kind of operations. What we don't know as much about in different basins, there's some of the details about like how flowback is handled. We've seen now different operators in the DJ Basin using these closed loop tankless systems. And we've seen those being very helpful in reducing VOC emissions, but we don't really have a good sense in other basins whether that's becoming more common or not. My sense is not so much, but I don't have the data on that.
Thank you very much.
Any other questions? All right. Well, thank you again, Jeff. We really appreciate your time. That was a wonderful presentation, and we will post the recording of this presentation on our website. So if you want to check on information you learned or share it with a colleague, we'll get it up in a few days here. But thanks again, and keep an eye out for future presentation announcements.
Thank you all.
Thank you.